All right. So today I will talk about the search for the stochastic gravitational background with PPTA, and especially with the second data release of the Parkes Pulsar Timing Array. So this work has been done on behalf of our collaboration, and I added some of the first most tier one co-authors to this slide, but it was really a collaboration effort. And yes, so my talk will be about the publication that is being reviewed at the Astrophysical Journal Letters. It's called On the Evidence for a Common Spectrum Process in the Search for Nanohertz Gravitational-Wave Background with the Parkes Pulsar Timing Array. And if you are interested, the policy of the Parkes Pulsar Timing Array is to only post papers to archive when they're accepted, which is, well, hopefully will be soon, but not the case at the moment. So if you're interested to have a look at the early draft, please send me an email. My email address will be on the bottom left throughout the presentation. So today, well, my talk will be consisting of 4 parts. So first, I will briefly describe what is Parkes Pulsar Timing Array and what it does, and then I'll very briefly describe the methodology without any equations or anything like that. Then I will discuss the common red process and what it actually is. And then I will go to spatial correlations, which is the spatial correlations is the signature of the stochastic gravitational wave background. All right, moving on. So the Parkes Pulsar Timing Array is an experiment which monitors an ensemble of 26 millisecond pulsars. And their sky positions are represented on the left of this slide. The arrival times are recorded with the Parkes Observatory, which has also been named Miriam, which is located in Australia, in New South Wales. And these circles on the left represent the sky positions of the pulsars, with the arrows representing their motion across the sky, and some other things, like the color, for example, represents the extension of the data set to the very early data at Parkes, and so on. And you can find more details in the publication, which I provided an archive link below. So what we do is well, I guess the main goal for the pulsar timing array is to detect the nanohertz gravitational background. So we time millisecond pulsars, and then we look at the time in spectra, which is basically going from arrival time measurement to the residual, and then residual is basically what is left when we subtract the arrival time from the expected arrival time, and then basically we take a Fourier transform, and then we can look at the spectra of pulsars. So on the left, you can see just an example image of how the spectra look like for pulsars of PPTA. And you can clearly see that there are 2 main features here. The first feature is the white noise, which is basically happens at high frequencies. And this basically looks like a flat power spectral density. And then there is a so-called red noise, which means that as we observe pulsars longer and longer, we start to observe some like stochastic drift of arrival times over many years. And this is what we call red noise. And it is represented by this diagonal lines towards the very low frequencies in the spectrum. And the lowest frequency is determined by the inverse of the total observation span, which is up to 15 years for the second data release of the PPTA. There are also, I will briefly mention that there are also other timing arrays. For example, there's a nanograph timing array and the European Pulsar Timing Array, and there are also emerging other PPTAs. So there will be the consortium of this Pulsar Timing Array is called the International Pulsar Timing Array, and C1 will have the next talk about the results of the International Pulsar Timing Array. Nicolas Cavallero will give a talk on behalf of the European Pulsar Timing Array on Thursday, and a few other people will cover the nanograph results as well. Well, yeah, so just to sum up this slide, first of all, we determine, well, the way we search for the stochastic gravitational background of pulsar timing arrays is first we try to determine if pulsars exhibit this so-called common red noise. So if all pulsars show timing spectra, at least, or at least if part of this timing spectra is has a certain slope, which is corresponding to the expected slope of the stochastic gravitational background, and then this, if they share the same amplitude of the spectrum as well, and then after we determine that there is a common part, we also look for spatial correlations in this common part. So far, around a year ago, the Nanograph collaboration reported basically the possible detection of the common red process, which is which means that there are some pulsars seem to share the same timing spectrum, which with the amplitudes and this power law index that is expected of the stochastic gravitational background, but there was no evidence for spatial correlations. In the work from Parkes Pulsar Timing Array, we do the same, and we try to confirm the Nanograph results. And indeed, this is what we do. So I will explain our results in the next slides. But in fact, we do also observe that pulsars, millisecond pulsars in the Parkes Pulsar Timing Array also share the same spectral properties. This is interesting because I guess the Nanograph collaboration is in the northern hemisphere and the PPTA is in the southern hemisphere. So I guess not all pulsars that are observed are the same. Some pulsars are the same, but some pulsars are new, and it's good to see that the result is consistent. However, we also try to come up with a, I guess try to look more like, try to look deep into the analysis and try to figure out whether it's really the gravitational wave background or it can be something else. And I guess this can be, well, definitely the future data sets will help to resolve this. And as we observe more pulsars, we will see the spectrum more clearly and so on and so forth. I guess with more pulsars, we have a better constraints on spatial correlation, so which is definitely a definitive signature of the gravitational background. But I guess it's good to compare the results and discuss this common spectrum in more details, and that's what I will try to do in my talk. All right, moving on. So now this is the slide that shows the spectral properties of this common spectrum process. So in PPTA DR2 we find very strong Bayesian evidence for this common spectrum process if we follow the same methodology that Nanograph used. So there are two figures here. The figure on the left shows the measurements of the amplitude and the power law index of this common spectral process. So the amplitude is on the y-axis and the power law index is on the x-axis. You can see that there is a dashed line represents the expected power law index of the stochastic gravitational background from supermassive black hole binaries, which is what is expected to be the first source of the gravitational waves detected with pulsar timing arrays. And the orange represents the Nanograph measurement, and the blue and gray represents the different assumptions under the PPTA measurement. And the interesting thing is that with PPTA measurement, we were able to infer the same, basically the same measurement, while Nanograph, under some different assumptions on the number of frequencies of the fluctuation frequencies of the timing residuals, they had a slightly different measurements. So that's one interesting thing. And then on the right, there is this different representation of the common red process measurement, which is basically the free spectral measurement. So we just assume that the different power at different frequency and just try to fit for this excess power. And you see that these measurements, which are in blue, they correspond, well, they match very nicely with this black line, which is the measurement that we have if you assume the amplitude and the power law index model. So this is basically what we have in terms of the spectrum. Now, there are also some interesting things that we can do is we can try to use the so-called factorized likelihood analysis, which was also done in the Nanograph work, and which is basically an equivalently correct way to infer the amplitude of the stochastic gravitational wave background if we assume the fixed power law index. And we basically just we just multiply the posterior distributions for different pulsars when fitting for this the red process with this fixed Pauli index, and this factorized likelihood approach is basically the thick blue line, and it matches. Oh, sorry, yes, and it matches really well with the direct measurement of the common red process amplitude when we don't use this factorized likelihood approach, when we just analyze an ensemble of pulsars together in a single likelihood analysis. And the orange is the nanograph measurement. And then the right is the dropout analysis, which shows that that all of the pulsars are consistent. Well, yeah, all of the pulsars are consistent with this having this common red process. And then some pulsars that are not very consistent are the pulsars actually with the strongest red noise. So I guess that's the takeaway message from this slide. Now, another interesting thing that was also explored by nanograph, and we approached this in PPTA at a slightly different angle, is that the effect of the solar system ephemeride errors. And it was suggested that these errors can mimic the stochastic gravitational background, for example. And I guess at first the fitting for the errors in solar system ephemeride basically was showing that there is some effect from solar system ephemeride errors, but the most recently discovered common red process is so strong that its evidence for it is much stronger than evidence for any errors in the ephemerides. And in the PPTA work, what we did is we actually tried to fit for every single component of this error in solar system parameters, which include the masses of planets that may affect the measurement, and each of the orbital elements of these planets. And the evidence is very small. There are some positive evidence for older ephemerides, but the evidence for common red process is much stronger. So it cannot be caused by the errors in the solar system ephemerides. Now the most interesting part. So we do, as we discover this common red process, which I will also explain some caveats in the further slides, but assuming that we do have this common red process from the stochastic gravitational background, we can fit for spatial correlations in different ways, and then we can infer correlation coefficients, and we can infer the amplitude of spatial correlations, and so on. So this is what is shown on this slide. On the left, there is a figure where we try to fit for the spatial correlation coefficients, and then the dashed line is the smoking gun of the stochastic gravitational background, which is the Hellings-Downs spatial correlation. It lines up really well, as you can see. However, we don't get any we don't get any strong evidence for or against the stochastic gravitational background, because the amplitude of the spatial correlations, which you can see on the right, is completely unconstrained. So it's in red color. So the common red part is the blue, and the red is the spatial correlated part, and this is completely unconstrained. And then I guess the interesting thing is that if we only fit for this, if we only fit for like this Hellings-Downs signal, we'll get a large evidence because of the overwhelming common red process part. So we have to separate it out, and we also always get always stronger signal for monopole and dipole spatial correlations. But that's I guess my take is that it happens because the monopole and dipole correlations have stronger requirements on spatial correlations, while, as you can see, the Hellings-Downs curve is overall closer to zero correlations, and we need to be careful by I guess fitting for this, and making sure that no excess noise leaks into that. But so far it's pretty safe because I guess the cross power it's very well separated from uncorrelated pulsar noise, but still this is a good thing to keep in mind. But then
1 minute.
1 minute, excellent. So I just during this minute I have an interesting highlight of our work, which is becoming a feature of our work, I guess. And we did some simulations, and I guess thought a bit more about the analysis, and we actually found that this common red process is not, well, it can be mostly caused by the rejection of the null hypothesis rather than there's some common signal present in the data. and we did a simulation demonstration to show this. So we need to, the takeaway message is that we need to be very careful about our priors for the noise, and then maybe a more detailed analysis will be happening very soon to follow up on that. So I guess, yeah, if you have any questions on this part, which I mentioned very briefly, please let me know or ask a question after the talk or email me. But I'm running out of time, so that's it. And thanks everyone for listening. Let me know if you have any questions.